reproduce it in the lab, but in the field it's very rare to observe a uniform flow. So most of the time the flows are non-uniform, okay? And this flow non-uniformity is characterized by transverse currents. You have transverse currents from the main channel towards the floodplain, or from the floodplain towards the main channel. And the question is here, what happened to the mixing layer? What happened to the turbulent vortices here when there is transverse currents? Okay? So for the people who know fluid mechanics, this structure are called Kelvin-Helmholtz instabilities, and it's mainly 2D horizontal structures. So I will speak about it. And last thing, this study was carried out in collaboration with Vladimir Nikola. Vladimir Nikola is a professor at Aberdeen University. So he's working with me on this topic. And this study is funded by this project. And I am the coordinator of this project with 11 partners from Portugal, Belgium, Germany, Switzerland, France, Norway, and that's all. That's all. So, which type of flows are we investigating? In fact, sorry, I let you take a chair. No, not me. No, I let you.
Settle down.
So the flow that we investigated are overbank flows, okay, but very specific overbank flows when they are subject to unbalance of stream flow conditions. Why? Do you have an idea? Flows with unbalanced upstream flow conditions, do you have an idea? In fact, when you are considering a river reach, usually you say, okay, this is one reach, another reach, and each reach is defined by an homogeneous geometry, homogeneous roughness, homogeneous slope, everything is homogeneous, okay? But here, I'm showing, for instance, an homogeneous reach, and upstream of this reach, there is a change in the geometry. So, for instance, here there is a diverging floodplains, here there is a converging floodplains, here there is a change in roughness. So, I want to say that when you consider a river reach, the upstream boundary, at the upstream boundary, the flow is always out of equilibrium. There is always unbalanced flow conditions at the upstream boundary of the river reach. And this is a picture of a dam in France. For instance, downstream of this dam, so here I can say, okay, this is an homogeneous reach, but here there is unbalanced flow distribution between main channel and floodplain. This disequilibrium will generate transverse currents. The transverse currents are the gray arrows here. So you could have transverse currents from the main channel towards the floodplains, from floodplains towards the main channel, and these transverse currents will interact with the shear layer turbulence, Kelvin-Helmholtz instabilities, vortices, and so on. So the situation is quite complex because we have in the transverse direction a lateral change in flow depth, a lateral change in roughness, because floodplain has a stronger roughness than main channel, and we have transverse currents. So it's very important to characterize these transverse currents. These transverse currents are characterized by a depth average transverse velocity. It means that there is a net mass exchange from one subsection to another. Stop me if you don't understand. So, second point of the context, these vortices, these coherent structures, they have been studied the first time by Selim in 1964 in the lab. Here you can see the main channel, here the floodplain, and you can see big horizontal structure here with the core at the interface between the main channel and floodplain. Here, this is a picture of the water surface with seeding. He put seeding on the water surface, and you can see the strong vortices here. And he has done a very interesting experiment. This is a compound cross-section. It's very small, but here there is isocontour of the streamwise velocities. You have the same flow depth here with the compound cross-section and here with the single cross-section. And what you observed, if there is no connection between the main channel and the floodplain, the conveyance in the main channel is significantly higher. If the reference situation is this, and you come to this situation, there is a reduction of the conveyance of minus 26%. So the existence of this coherent structure or not, they can exist or they cannot exist. It's very important to know when they exist and when they do not exist, because it affects the conveyance of the river. Okay? So this was measured under uniform flow conditions. Uniform flow conditions. It means that there is no change in the streamwise direction. No change, no transverse currents. So, my question is, what is the effect of transverse current on the turbulent mixing layer? So the turbulent mixing layer, we are used to separate the mean flow and the turbulence statistics. So we will see the effect of the transverse current on the mean flow, on the turbulence statistics, and I will show you also what we call the Kelvin-Helmholtz coherent structures. And to be clear on transverse currents will be characterized by the depth average mean transverse velocity. This is the integration over the depth of the transverse velocity, okay? D means depth average. And it's important to recall that under uniform flow, UID is nil. Okay? Yeah. Why it is quasi 2D? Okay. Here, if you look at this picture, you say, oh, it looks like a 2D structure. But you have a water surface and you have a bottom. So it is not invariant in the vertical direction. You have an influence of the bottom, and you have, so it is a shallow, okay? So compared to plane mixing layer, you have an influence of the bottom, and it's not completely 2D. 2D would mean that there is a 2D would mean that the structure has the same shape in the vertical direction. It's false, because over the bottom, when reaching the bottom, they vanishes. There is no structures on the bottom. You see what I mean? Big structure at the water surface, and it decreases. But they have a vertical axis. Okay, it is turning like this. That's why we are saying that this is 2D, but quasi 2D because there is an influence of the bottom. So my beautiful flue. So this is the compound channel flue in the lab at SDA, 18 meters long, 3 meters wide. So we put some artificial floodplain here. This is a cross section. Each floodplain is 1 meter wide. The main channel is 1 meter wide. And here, so the total width is 3 meters. And here, what we call the bank full stage in the main channel is 11.7 centimeters. 11.7 centimeters. So the green floodplain, in fact, we have put some artificial grass over the floodplain. The artificial grass, the height of the artificial grass is 5 millimeters. And in the following, I will use these dimensionless coordinates. BF is the floodplain width. So the longitudinal and transverse coordinates are normalized by DF. And the vertical coordinate is normalized by the flow depth in the main channel. DM is the flow depth in the main channel. Okay? And go on. So, I said that the transverse currents are caused by unbalanced inflow conditions. So here we are using 3 inlet tanks, one for the left floodplain, one for the main channel, and one for the right floodplain. QM is the discharge in the main channel, QF is the discharge in each floodplain. Okay? So for each tank we have an independent pump, an independent flow meter, and here we are studying 4 flow cases. What is important to note, we are working with a constant total flow rate. So the total flow rate is 140 liters per second, but what is modified is the distribution between the main channel and the floodplain upstream. We can generate an excess in floodplain inflow or a deficit in floodplain inflow. If you put an excess in floodplain inflow, there will be transverse currents from the floodplain towards the main channel. If you put a deficit in floodplain flow, the main channel will give water to the floodplain. So the transverse currents will be in the opposite direction. So, the case 8 liters per second, with 8 liters in the floodplain and 98 in the main channel, it's a uniform flow. There is no transverse currents between the main channel and the floodplain. This is our reference flow. Case 8 liters is the reference flow. For the case 4 liters per second, with a deficit in floodplain inflow, we generate transverse currents toward the floodplain. The floodplain needs some additional water. And for these 2 flow cases, 12 and 16 liters per second in the floodplain, we are generating transverse currents toward the main channel. Do you understand this? Okay? So what we are measuring, first we are doing some 1-point velocity measurements. So I'm using a side-looking ADV probe. For each measurement, the acquisition duration is 300 seconds. At 100 Hertz, it means 30,000 samples. I'm using the despacking of Goring and Nicola. And what is more interesting, to catch the coherent structure, is the 2-point velocity measurements. So I was not used with this kind of measurements, but Nicola was used to this measurement. So he gave me his knowledge. He helped me to do this. And we have 2 flow configurations. So this is the floodplain, this is the main channel, and this is the interface between the main channel and the floodplain. First, we are doing measurements across the river. So in this case, the ADV probes are in line with the lateral direction. This probe is measuring this probe is fixed. The first probe is fixed, is measuring at the interface, and the other probe is going across the river. Okay, I am moving it. Okay, so this is the first, so here a small distance, here a larger distance, and so on and so on. And this is the first flow configuration. In the second flow configuration, ADV probes are in line with the longitudinal direction. And I am measuring, for both probes, I am measuring at the interface. So the fixed probe is measuring here, and the downstream probe is going like this, is going down the river, okay? But they are both measuring at y star equals to 1. They are both measuring at the interface. You know this spiking? In the signal of the velocity, sometimes you have very high spikes, and this is only noise. And the despiking of going Nicola remove these spike values because it artificially increase what you are measuring, and it's only noise. So some results. The first results, the contrast. Do you see the purple dye here from here? The contrast is not so good between the green and the purple. But here we are injecting potassium permanganate. We are injecting potassium permanganate with a pitot tube here, and as you can see, this dye will move, and here we can clearly see that there is an ejection of flow from the flood plains towards the main channel. Here we can see a wave. This wave is called the Kelvin-Helmholtz instability. Okay? This is due to the difference of velocity between the floodplain and the main channel, and some people told me that the waves over the sea, this is the same phenomena. This is a difference of velocity between the wind and between the sea. The difference in velocity between the wind and between the sea generate waves, and a wave is a Kelvin-Helmholtz instability. So we can measure the period of this instability, and in this case it was around 4 or 5 seconds. So if we compare two cases, this is the case 4 liters per second, and this is the case 8 liters per second. For the case 4 liters per second, the velocity difference between main channel and floodplain is huge. For this one, sorry. So there is a high velocity difference between both subsections, and here the velocity difference is smaller. And you can see that the instability is larger here. The amplitude of the instability is larger here. It means that the coherent structure will be bigger here than here.
On this basis, you have selected the standard figure, 8 liter per second.
Sorry?
On this basis, you have selected the standard figure, discharge at floodplain 8 liter per second.
No, it was, I have chosen QF before these measurements. I selected it. Okay. My reference flow is this one. This is uniform flow. I don't have the choice. There is only one value that works. This is 8, and so okay. So what I want to have is symmetrical things. So here, minus 50% plus 50%. Okay? And then plus 100%. I have also QF equals to 0. It is a jet. A jet, if there is no flow in the floodplain, this is a jet from the main channel, but I'm not showing this result here, okay? So it's just to have two symmetrical deficit equal to excess, and a strong flow towards the, you understand? But look at the difference in velocity. This is the main channel velocity and floodplain velocity. This difference is huge here and very small here. So the coherent structure will be stronger here than here. So, okay, so the first step is to look at the uniform flow. So, a compressional flow presents a mixing layer, and in the literature, the first thing to measure when you have a mixing layer is the mixing layer width. The mixing layer width, delta, you have several formula in the literature. I'm using this formula of Van Proijen. Sorry. So here you have y 0.25 here. Here you have y 0.75, and delta is equal to 2 times this difference. This is the mid flow. This is not the turbulence. This is the mid flow. And here I'm showing the results. This is the longitudinal position, and this is delta. So I have a question for you. Is it my flow uniform? Is it uniform in the streamwise direction?
No.
The mixing layer is changing. Maybe here it slows down,
Velocity.
but I'm not sure that it is. And what is interesting is to see the two boundaries. Here, I don't know if you see it. This is y 0.25, this position, and here this is y 0.75 and y 0.25. What do you see? What do you see on these two lateral boundaries? There is no stabilization of the mixing layer in the main channel. It is still developing until the last measuring station, but here this is quite stable. And I give the explanation here. The confinement is very strong in the floodplain. There is a shallow flow, deep flow in the main channel. So there is a stronger influence of the confinement. First, of the flow depth, and second, of the bed-induced turbulence. And it was analyzed by Xu et al. In 1988. So here you can stabilize your mixing layer, but not here. So I'm very proud to have 18 meters long flume in glass, but it's not enough to study a uniform flow. So we were very disappointed. So regarding the turbulence statistics, this is the same thing. So look at this first plot. I will present you the following after. Look at this first plot. This is the fluctuation. U prime is the fluctuation in the time of the U prime y is the fluctuation in the time and the transverse velocity. So this is, we call it also a turbulent intensity. And this is a transverse profile. So here you have the main channel and floodplain interface. And this is the X position. And we can see that there is a development of turbulence, especially in the main channel, until the last measuring section. So the flow is not uniform based on turbulence statistics. And now, I don't know if you are used to this space-time correlation. I was not, but now I'm aware of this. It's very simple. You are measuring the signal at two different positions with the two props, and you multiply the two signals, okay? And if the signals are independent, the time average of this product will be 0. If the two signals are not independent, if they are dependent, this product will be different from 0. Okay? So here we have a dimension, a normalization. a normalization, and tau is a lag, a time lag between the two side node, and epsilon k is a spatial lag. So this is what we call a space-time correlation.